One type of shape that arises naturally and that is best analyzed in terms of polar coordinates is a spiral. So if you use polar coordinates and you set r equal to theta and you trace that out, you get a spiral like this. So you start at a radius of 0 and an angle of 0. Then when you wrap around from 0 to pi over 2, your length increases to pi over 2. And then here your length would be pi, 3 pi over 2, and 2 pi. So this is a nice simple spiral. What I would like to do is try to figure out how much area is inside of this curve. So as you move through these different quadrants, I want to figure out how much area is trapped inside of this curve, and I'll stop it right here on the edge at theta equals 2 pi. To figure out how to calculate that, I'm going to go back to ideas that you've probably used before with integrals in applications. I want to approximate the area in some nice way that allows me to extend that approximation to an integral when I let the number of pieces that I'm using go to infinity. So I want to do something where I'm like breaking this up into some nice simple geometric objects. If I do like 5 of those objects, I should get a rough approximation. If I do 10 of those objects, I should get a better approximation, and each object should be smaller. And if I take the limit of that sequence of approximations as the number of pieces goes to infinity, or as, let's just say as the number of pieces goes to infinity, I should get the exact area. So a way for us to do this is I'm just going to try to set up a more general function than this one. So let's say I'm starting at theta equals a, and I have some radius, and then as I wrap around, I'm going to draw it like the radius is extending as I move out, as I sweep theta around. So something like this, and then I'll stop it at, let's say, theta equals b. And then I want to get an approximation for this area using pieces. And my most natural, simple geometric pieces to use here are going to be wedges. So I'm going to break this up into pieces. I'll use 3 pieces to start out with. So on my first piece, I'm going to use the radius that takes me to this point, and then just wrap around. And I'll be able to calculate this area nicely with the good old formula from trig. Then my second piece will look like this, and my third piece will look like this. That will give me a good approximation. I'll get better approximations if I use more pieces but use the same process. So first, I have to remember how to calculate the area of a wedge like this. And basically what I'm going to do is take the area of a full circle, pi r squared, and then multiply it by the ratio of how much angle was swept out divided by a full rotation. So that would be an angle of theta over the full rotation 2 pi in radians. And usually people will write this as 1/2 r squared theta. Probably have memorized that at some point. So I'm adding up wedges like this, where r is changing and r depends on theta, and I'm sweeping out a small amount of theta. So I'm gonna let the amount of theta that's being swept out be called delta theta to represent a small change. Then the total area here is approximated by just adding up those pieces. This is delta theta, and again, this radius depends on where I'm at. So I might think of this as like theta 0, theta 1, theta 2, and then I would sum from like I equals 1 to n. Here it would be I equals 1 to 3. And this would be I could call it Ri, or R of theta I. Thinking of R as a function of theta. When I let this number of pieces go to infinity, it's the same as letting this delta theta shrink down to 0. And so when I do that, this pops into an integral. The function that I have here to integrate is 1/2 r squared. And I'm going to emphasize that r is a function of theta. So I could write this a little differently. Maybe you would write like r equals f of theta. This would be 1/2 f squared. Then the delta theta becomes d theta. So if I want to look at this area now, I should be able to get the exact area by applying this formula. And in this case, my r of theta is just r of theta equals theta. So for that example, I'm going to integrate from 0 all the way around to 2 pi. I'll go ahead and rewrite what r is in terms of theta. And then just find the antiderivative and plug in. And the bad thing about this example is that you probably have never calculated this area before, so when I get an answer, it's not like it will confirm what you had already suspected or what you already knew would be the correct answer. So you just have to take my word for it on this one. But we could also use this formula to calculate the area of a circle. We already know what that should be. So it's a good exercise to take the same formula and use like r equals 5. So you have a circle of radius 5. Make sure you do get pi times 5 squared for your answer here in that example. I'm getting 1/6 theta cubed from 0 to 2 pi. So theta cubed becomes 8 pi cubed. So I'm getting an area of 4/3 pi r cubed inside this spiral. If you've played around with polar coordinates and different kinds of functions that can be represented with polar functions, you know that there are unique shapes that you can't describe without using polar coordinates usually. So this formula is very helpful in those contexts.